All right, so in this video, we're going to take a look at some of the ALEKS topics from the chemical reactions and chemical equations. First question takes a look at stoichiometric coefficients, and it asks you what is the total number of oxygen atoms on the left-hand side of this chemical equation. So a couple things to keep in mind when we have these chemical equations, at least the ones that we're starting off with. So I'll just copy and paste this over here. So you'll notice when you read this chemical equation that there are several things that are on here. So obviously you have, for instance, the chemical formulas for the compounds involved or the elements involved. And then in front of the formulas, you also have these small whole numbers. So the 2, the 4, the 12, the 4. When you don't see a whole number, 1 is understood to be there, and then 12. Those are coefficients, and they multiply everything that come in the chemical formula by that coefficient. So for example, if it's asking you for the number of oxygen atoms on the left-hand side of the equation, so we're looking here on the left side, which is that's the reactant side, and we want to count the number of oxygens, number of O's. All right, so we have in the chemical formula, calcium phosphate, we have 4 O's times 2. So we have 4 of these oxygens times the substitute on the outside. So that's 4 times 2 is 8. We also have 2 of that entire thing. So 8 times 2 here from the calcium phosphate would give me 16. And my SiO2, I have 2 oxygens times 4. So 4 times 2 is going to give me 8. And the carbon obviously doesn't have anything. So 18 plus 6 will give me a total of 24 O's on the left side of this equation. So you want to pay close attention to the chemical formula in each case, all right? And you want to pay attention to the subscripts. So we have 4 O's times the subscript on the outside, which is 4 times 2 is 8. And then we need to account for any coefficient. We times it by that to get the total number. So 24 here would be the total number of oxygens on the left side of this equation. All right, so in the next question, we'll take a look at balancing chemical equations. And when we balance chemical equations, the whole point of doing that is to make sure that we have the same number and types of atoms on the left side, on the reactant side, compared to the right side, which is the product side. All right, so good strategy here. We start off, we rewrite the question. We can omit the state symbols right now because they're not important when it comes to balancing. And then what I like to do is just put a line in front of each of the formulas so I know exactly where the coefficient is going to go. All right, and then I'm going to list each of the atoms that I have. So I have iron on the left side, and on the right side, I have oxygens on the left and on the right. And I'm just going to count now, just like we did in the previous question, how many of these we have. So on the left side here, we have 2 irons, and we have 3 oxygens. On the right side, we have 1 iron, and we have 2 oxygens on the right. So when it comes to balancing, really, it's just a trial and error that you're doing, but there are some strategies that you can use to make that trial and error go by a lot quicker. So for right now, if you wanted to do this step by step, what we can see is if I want to make 2 irons on the right side, okay, I can put a 2 in front of the Fe. So 2 times, remember, when you don't see a subscript, 1 is understood to be there. So 2 times 1 is going to give me that 2 irons. Now I need to balance my oxygen. So I have 3 on the left side, and I have 2 over here on the right. So obviously 2 doesn't go into 3 and a whole number of times. So when you run into a situation like this, you have 3 and 2, you want to try to get the lowest common multiple of them. So the lowest common multiple of 3 and 2 would be 6. We want to make 6 oxygens on the right, 6 oxygens on the left. So to make 6 oxygens on the right side, I would put a 3. So 3 times 2 is going to give me 6 over here. And then to make 6 on the left side, so 3 in the oxygen times my coefficient should give me 6. So 3 times 2 is going to give me 6. However, when I put this coefficient in front, I also multiply my irons by that. So 2 times 2, change my irons now to 4. I need to make 4 irons on the right, so I need to change my coefficient there to make 4 irons on the right. Oxygens are good, irons are good. That's my balanced equation. The thing to note about balancing equations is the only thing I've been changing or I've been manipulating are the coefficients. Okay, that's the only thing that you can change when you balance equations. You cannot change subscripts. You cannot insert numbers in the middle of formulas. You can only change coefficients. All right, so in this question, similar to the previous one, except now it looks a little bit more complicated, but we're going to follow the same steps when it comes to balancing, right? So I'm going to just put a line in front of each of these so I know where my coefficients are going to go. And then I'm just going to count how many of each of these things we have. So identify the atoms you have on both sides. I have carbon, I have H, and I have O on both sides of the equation. And then we're just going to count them. So on the left side, I have 1, 2, 3 carbons. On the right side, I have 1. On the left side, I have how many H's? 3 H's, 4, 5, and 3. 8 H's on the left. On the right side, I have 2 H's. On the left side, I have 2 oxygens. On the right side, I have 2. And then I have the 1 here from the H2Os. I have 3 O's on the right. So when you see a situation like this, where the carbons are all found in one place, they're in one molecule here, one compound on the left, they're in one compound on the right. The hydrogens are in one compound on the left and in one compound on the right. But the oxygens, one compound on the left or one substance on the left, but now it's split between 2 different places. So a good strategy would be to leave the oxygens to the last when you balance. So we can balance the other things first, okay? So if I have 3 carbons on the left side, I need to make 3 carbons on the right. So I'm going to put a 3 in front of the thing with the carbon. So now 3 times the 1 carbon here is going to give me 3. But now I've changed my oxygen. So 3 times 2 is the 6, plus the 1 here from the O would give me 7 O's, right? Remember, we're leaving the O's to the end to balance, but when you change your coefficients, don't forget that you change everything that comes in that formula. On the left side, I have 8 H's. I need to make 8 H's on the right. So I have 2 H's here to start with. So 2 times what gives me 8? 2 times 4 is 8. But by putting this 4 in front, I also now multiply the O here. So we have 1 O in the H2O. 1 times 4 is going to give me 4, plus the 3 times 2, 6 O's from the CO2. 4 plus 6 is going to give me 10. Okay, so I've balanced my C's, balanced my H's. Now my O's, I have 10 O's on the right side in total. I need to make 10 O's on the left. Well, the O is only found here. So 2 times what gives me 10? 2 times 5 would give me 10 O's. So that's your balanced equation, or the coefficients that would provide this balanced equation. For the first compound here, we didn't put a coefficient. 1 is understood to be there. All right, so in this question, we're taking a look at recognizing reduction versus oxidation reactions. And there are a couple things we can look at when it comes to reduction and oxidation that we can try to find in the formulas. So the one thing you want to keep in mind is that if you know all the characteristics of oxidation, well, reduction is just the opposite. Or if you know all the characteristics of reduction, oxidation is just the opposite. All right, so we can look at maybe one of these, and then we'll just figure out what the opposites are. So reduction could mean gaining H's, which mean oxidation then is the opposite of that, would be losing H's. Reduction can mean losing oxygens, which means oxidation would mean gaining O's. And in these chemical formulas, you will see a bunch of H's and O's. And the element in red, we're trying to see whether that element either gained H's or lost H's, gained O's or lost O's. The other thing that we can observe or try to decide is reduction could mean the charge becomes more negative. And really, it's not strictly the charge, it's something called the oxidation number, but we'll use charge for right now. So the charge becomes more negative, which means in an oxidation, the charge is going to become more positive. So it increases, in other words. Whereas in a reduction, the charge decreases. Okay, so we can see a combination of these. We can maybe just see one of them. So in the first one here, we can see the nitrogen starts off on its own, and then at the end, it has hydrogen added to it. So this nitrogen here has gained hydrogen, right? Didn't have any H to begin with, had H's at the end. Gaining hydrogen would be reduction. The carbon here in the second one is on its own. According to this reaction, it ends up with oxygen attached to it. So this has gained oxygen. That would be an example of oxidation. Let's jump down to the last one, and we'll come back to the third in a second. So the sulfur down here starts off being attached to hydrogens. Then at the end, the sulfur is on its own, right? So it originally had H's attached to it. Then it's lost those H's. So losing hydrogen would be an example of oxidation, which is what we have here. And then in the last one, I'm sorry, the second to last one, we'll see here that the sulfur starts off being attached to hydrogens, and then here it ends up being attached to sodium. So you may think, well, since it's lost H's, should it be oxidation? Well, here, because it's attached to something else at the end, we need to take a closer look at it. All right, so we have H2S, and then it becomes Na2S. So we can look at the charges of sulfur in both of these cases. So at the beginning here, right, the sulfur has a charge of 2 minus, and we know that because hydrogen is always going to be the +1. All right, and we have 2 of the hydrogens, so times 2 would give me a total charge there of +2, and then the sulfur has to be -2 to cancel that out. At the end, the sulfur here, if we don't know what the charge on the sulfur is, we can look at the sodium. Sodium is always +1. We have 2 sodium, so that's +2. Well, the sulfur there has to be then -2 to cancel that out. So in this case, the charge on the sulfur doesn't change. It starts off as -2, ends up as -2. So it's neither reduced nor oxidized in that case. So in some cases, it's pretty obvious to see whether it's lost or gained hydrogens or oxygens. In other cases, we need to take a look at the charges. All right, and here we want to recognize or be able to pick out from a lineup these different types of chemical reaction. Recognizing the types of reactions. And if you haven't done this already in lab, you will be doing this. You'll actually be performing several of these reactions in the laboratory. So let's take a look at a couple of these. So in the first one, we have calcium plus chlorine. I'm going to omit the state symbols just for simplicity's sake to give calcium chloride CaCl2. So in this case here, what we have are we have more than one reactant. So we have 2 different reactants in this case, and we only have one type of product. So in other words, what's happening is those reactants are coming together. They are combining to make one product, one type of product. So this would be an example of a combination, or sometimes it's called a synthesis reaction. Okay, and that's the hallmark state is we have more than one reactant combining to make one type of product. In the second one, we have FeCl2 reacting with BAS to produce BaCl2. And then we have FeS. So recognizing the types of components we have in the chemical reaction is going to be your clue. So here we have two compounds, two different compounds, and we end up with two new compounds, right? The combinations are different. And whenever you see that, that's a telltale sign of a double replacement reaction. Okay, and what's happening here in a double replacement, usually the metals are the things that swap places with each other, right? So I have my Fe. Think of the Fe and the Ba, the Ba, that swap places. So the Fe was originally with the Cl, now the Fe goes with the sulfur to make Fes. The Ba was originally with the sulfur, the Ba now goes where the iron was to make BaCl2. So that would be a double replacement reaction. And then in the last one here, we have H2SO3. Okay, so we have one compound to begin with, one type of a compound to start with. And then this becomes H2O, and then it becomes SO2. So we have two types of products, or more than one, would be a more generic way. So we have one thing to start off with that breaks down to two or more things. What's happening there is that that initial reactant is decomposing. So it would be an example of a decomposition reaction or breaking down. All right, so the next one, we're looking at predicting the products of a combustion reaction. All right, so combustion reactions typically mean reaction with oxygen. Okay, and if you have a carbon-containing reactant, that usually means the products are typically CO2, carbon dioxide, and we get H2O, water as the other product. So in this reaction here, we have our carbon-containing reactant reacting with oxygen. So CO2 and H2O will be our products. We would just need to make sure that our equation is properly balanced following the strategy we talked about previously, right? So when we go through and balance this particular one, we'd have the smallest whole number coefficients that would balance our equation. So combustion, if you have a carbon-containing reactant, it's just reaction with oxygen to produce CO2 gas and H2O gas. All right, so in this question, we're looking at predicting the products of a single replacement reaction involving hydrogen. Okay, so in a single replacement reaction, typically what that means is you have an element to start off with that reacts with a compound, which is just two different elements combined together, or multiple elements combined together, to produce now a new element on its own, and we get a new compound. Okay, so in the case of these that involve hydrogens, so if I have my element now, barium, reacting with HNO3, in a single replacement, what usually occurs is you either have a metal, in this case barium, that takes the place of another metal or substitutes another metal, or in our case, it takes the place of the hydrogen, right? So it kicks out the hydrogen. Hydrogen now goes on its own and forms elemental hydrogen, which is H2. And then the barium now combines with the remaining part here, the nitrate, to make our new compound, BaNO3. And then we need to make sure that this formula is written correctly. Nitrate is always 1-, barium is always 2+. So we need two nitrates to balance out the barium that we have. Okay, so that's your single replacement, also known as substitution reactions, where you typically have a metal replacing another metal, or in this case, a metal replacing hydrogen and liberating H2 as a new element, we make a new combination between the original metal and the remaining part of the original compound. You just need to make sure that that formula is correct, and then you would balance your equation to ensure that we haven't violated the law of conservation of matter.